Ladies and gentlemen, thanks for appearing, such large number. May I introduce to you Greg from Berlin. He's going to tell you about non-obvious bugs by example, and don't want to make it long. Greg, thank you.
All right. Hi, everyone. My name is Greg, and the title of my talk is Non-Obvious Bugs by Example. I think we can just dive in. So what are we going to do here? We are going to see non-obvious crypto-related bugs in two more or less well-known content management systems. And those bugs are, as most crypto bugs, quite easy to make and hard to spot, which makes them interesting to exploit, interesting to hunt down. And I hope it's going to be some fun for you. Okay. Yeah, I think we can quickly skip over that one. We'll discuss the whole process from the discovery till the exploitation of the two bugs I have here. Like, right exactly the way I originally discovered the bugs. So first of all, the code part that raised the suspicion, then some observations, technical background analysis, and of course the exploit and some demos. Okay, so the first one. The first one is in typo 3, which I guess most of you know. It's already fixed, so no order here. What are we looking at? Well, typo 3 has this functionality that allows you to download arbitrary files from the server. Like just to offer, I don't know what type of downloads to the user, MP3 or something, I don't know. And this is done by using a URL like this. So you basically supply this jump URL parameter, select the target file name, and you also need to supply this hash value here. This hash value is then internally verified by typo 3 somehow, and then it decides whether or not it's going to grant you access. So that looks interesting. Let's look at the source code. So the source code is here. We can basically see that they built some array here. Oh, that's PHP code, but I guess you guys should be able to read PHP, right? So they built an array here containing the jump URL parameter, some other junk parameters, some config setting named encryption key, and then they MD5 the whole array and compare the resulting hash with the hash that you actually supplied in the URL. Okay, so this is how it works. Yeah, that summarizes it. So to calculate the hash, they use a secret variable encryption key. So as we don't know encryption key, we are actually unable to supply the correct hash value they use here. So that looks somehow sane. As a side note, what they probably actually wanted to do is to build some message authentication code using the secret key that they have in the config file. This is done improperly here because they just appended the encryption key at the end. It's not so important, and this is not a crypto class, so just to mention it, don't do it at home. Okay, we have seen the code, this short MD5 function, which I told you does some MD5 hashing. So what they actually do in short MD5 is they compute the MD5 of their input, and then they build a substring. And by default, here the len parameter has a default value of 10. They select 10 hex characters, which is 5 bytes, which is 40 bits. And here's another observation. In general, it's okay to shorten hash or MAC values. But first of all, why? Because in this case, bandwidth shouldn't be the problem. I mean, it's a couple of bytes only. And second, 5 bytes is not that much. Okay. So what we have seen so far actually seems to make sense somehow. It's not pretty obvious how to attack or break the scheme, and this is where some PHP specific interesting properties come into play. The two values are compared using the double equals operator you see here. And as a regular sane programmer, you would probably think, yeah, okay, if you compare them using the double equals operator, well, it checks if they're equal. For PHP, this isn't so true. In PHP, this operator is not type safe. That means it's going to perform some typecasting before it actually compares the values that you supplied. Okay, let's see how it works. This is from the PHP manual. And now sit tight. The first line, I mean, I guess the first line is somehow acceptable. The number 0 equals to the string A because, you know, you can't cast A to a number, and so it returns 0 probably. Okay, I mean, why not? The second line is a bit more interesting. Here you can see that that it will convert strings to numbers before it compares them if the strings look like numbers, which doesn't make sense at all because those two strings here, I mean, they don't even have the same length. And in my world, strings that don't have the same length are not equal. For PHP, they seem to be. And especially interesting is probably this line here, the third one, where it says the string 10 equals the string 1E1. So as most of you probably know, that's scientific notation. Probably I don't need to mention here. So this is 100, 10 even, sorry. So this is 10, but considering those two strings equal is really interesting. Okay. So what do we make of it? The basic idea is, what happens if the computed hash looks like O, E, and then some numbers? That's a valid numeric string. That's also a valid hash value, considering the hex digits. O, E, and then only numbers. That's valid ASCII hex. And that would be the numerical value 0. So the equals operator would think, okay, this string and the string containing only the O character are equal. Okay, so what we actually need to do is we need to influence the computed hash to take it to make it take the desired form. So because then it would be equal to 0, and we could just submit 0 as our submitted hash value, and it would let us in. The question is how to modify the computed hash value. Of course, we cannot arbitrarily set the value, because then we could just supply the value we just set, and that'd be too trivial. But we can still influence the computed hash. One way to influence it is we could just append some junk string to the jump URL parameter, because it doesn't need to be canonical. So we can, for instance, just append, I don't know, // that wouldn't change the file name at all, and but it would change the hash value. So as we now know that we can at least influence the computed hash, how probable is it that we are actually going to hit some hash value that we like? Okay, let's assume the first byte needs to be OXOE, and the following nibbles all need to be numerical. That is only from 0 to 9, because otherwise PHP wouldn't consider it a string. If it, I don't know, if there was some A or B, C in it, sorry, did I say string? It wouldn't consider it a number. So if there were any letters in it, then PHP wouldn't consider the resulting string numerical. Yes, so let's further assume that MD5 generates a random distribution. I guess for this use case, it's okay. So we have 16 values for each nibble, and 10 of them are okay. And that is the chance of 5 by 8 that a nibble is numeric. As all the nibbles are independent, the overall chance that we get is 1 by 256 for the first byte, which needs to be OXOE, and then 5 by 8 to the power of 8 for the remaining 8 nibbles, and which is about 0.009 something percent. And that means, in average, we need about 5K tries before we hit a good hash value. And that's not terrible much. And actually, it's even less because values like OO, OE, blah are also okay. But we don't even need to consider them because 5,000 tries is nothing. You can do it from your DSL line or something. Okay, so the attack is pretty straightforward. You just submit multiple requests for the same file, say etc passwd. And for each request, you modify the file name or some other parameter so that the hash value will be different. And as your submitted hash, always choose 0. And then you get some hot drink and wait for your file. And to make it even worse, there is some other minor issue. The secret key that it uses is stored in a file named localconf.php. And the code should actually make sure that under no circumstances you can download localconf.php. Well, if the magic quotes setting is disabled and magic quotes is deprecated since PHP 5 something, I don't know, then this check doesn't work. And if you submit a file name like this one here, so you basically insert a 0 byte here, poison 0 byte, then you will be able to download localconf.php, which contains the encryption key that you need to use to calculate correct hash values. So once you got it, you can calculate like legitimate hash values and get any file you want in one try. Okay, I think, yeah, it's time for a demo. I got a local typo 3 installation here, so we can just use my demo script on this system, so we don't need to attack any computer on the internet. So, as you see here, typo 3 runs on localhost, and I want to get etc passwd, and now it's submitting requests with modified parameters to influence the hash value. And I hope it doesn't take too long, because my system is kind of slow. Only an average. We can hope that we're lucky.
You're doing it sequentially?
Oh, here we go. Yeah, I'm doing it sequentially because I'm lazy. Lazy hacker is lazy. For a real weaponized exploit, you'd probably not do it, but I mean, who cares? Yeah. So here we go. This is my passwd. Lucky me, the real passwords are not here. Okay, so you see it works. You see I can retrieve arbitrary files from the server, and that should probably be it. So this was the first bug. If you like this one, you should sit tight for the second one, which is even more fun. And this one is actually Ode, because the Joomla guys, for I don't know what reason, don't seem to be able to fix it. Okay, so what are we looking for? When you read the Joomla code, then you stumble upon this one function named getRandomPassword. And getRandomPassword looks interesting because password generation is always interesting. And this is what the function does. So I guess the most important parts are here. It seeds the random number generator with some CRC value that is obtained by using the output of microtime and the output of stat And then it uses the seeded random number generator here and requests random numbers and uses the random numbers to assemble a password out of this alphabet here. Okay, so this is what it does. In PHP, the MT underscore functions are random numbers, give you random numbers from the Mersenne twister, which is one particular random number generator implementation. And this one is only seeded with 32-bit values. That basically immediately means that for any password length that you fix, you only have at most 2 to the power of 32 different passwords. They reseed their generator for every time they generate a password, and that's not exactly smart, because actually you should reseed, or you should seed the generator once and then use it. And actually you shouldn't seed it at all, because the operating system or someone should care. And the seed is obtained using the CRC32 that we've seen. This is interesting because the input of CRC32 is kind of static. The only thing that really changes there are time fields, because they used microtime and the output of stat. And stat returns file modification times and stuff, and microtime obviously returns time steps. But CRC32 is not really a cryptographic function, so maybe we can find some way to predict the seed. Okay, even if we were able to predict the seed, what would be the impact? Because that looks a bit more difficult than the typo 3 one, so it's probably worth first analyzing where this is going to lead us. The gen random password function is used in a couple of places, including the password reset functionality of the Joomla installation. So if you're too dumb to remember your password, you can click this button, hey, I forgot my password, please send me a token where I can reset my password. And then you get a token via email, and you can use this token to reset your password to someone that you can better remember, hopefully. And that seems to be an interesting attack vector. Reset the password of the admin account and then overtake the whole site. Or probably even use it to upload, I don't know, a web shell or further attack the system. So it actually seems to be worth looking a bit deeper into the implementation they use here. To generate this password reset token, they use a function named getHash. And getHash uses a value, which we can see here, named config.secret. And this is kind of similar to what they have done in typo 3. They also use some secret installation-specific key to generate cryptographic secrets. So this is a scheme implemented quite often. Config.secret is generated during installation process of the Joomla instance. And guess how they generate it? Of course, they use gen random password. What else? Reading their view random would be too lame. So take gen random password for it. So what have we seen so far? The password reset function generates tokens and sends them out via email. It uses randomly generated strings as tokens and also an installation-specific secret key. So even if we could predict the random number generator's output, we would still need to know this secret key. That looks interesting enough to spend some more time. And here we go. First of all, let's look after the secret key. Because config.secret is also used in quite a number of places. For instance, when you click the Remember My Password button because people who tend to forget their passwords like the browser to remember the password in a cookie or somewhere, and to actually set the authentication cookie, they use the, where do we have it? Oh yeah, they use the getHash function, which then again made use of the config.secret value. Let me go back 2 slides. Here, getHash makes use of config.secret, and getHash is also used when setting the authentication cookie that implements the remember my password function. Okay, so what they actually set here is MD5 of config.secret plus the string jlogin_remember. Okay, good. So this is the password remember cookie. Well, at least they don't directly leak config.secret in here. So the question is, how can we extract config.secret from the cookie that was set? Okay, we know config.secret was generated during the installation process using this genRandom password function that we've seen. There are only 2 to the power of 32 possible passwords, because we have only 32 bits of seed for the random number generator. So there can't be more passwords. We could just build some table to look up the seed based on the token that the Joomla instance gave us. The table would cost us 2 to the power of 32 memory and 2 to the power of 32 time. And we could actually optimize it using rainbow tables, but then again, I'm lazy and I didn't do it. And actually, generating those tables was painful enough because I did it on company hardware. My company allowed me to use company machines for it, and as you see, my netbook is not the right equipment for generating large cryptographic data sets. So I used company machines, and I let it run for a couple of days. And suddenly my boss walked up to me and said, "Hey, you're running this crypto stuff there." Yeah. I need to tell you something. Our RAID crashed. I was like, "No, it didn't. Did it?" "Yeah, it did. You actually managed to stress the hard disk so much that the RAID crashed." Actually, it was the fault of the hard disk manufacturer, because they had buggy firmware on the hard disks, and under certain stress, the hard disks would just disappear from the RAID. So anyway, this is a great stress test and benchmark for your hardware, and I can only encourage you to try it on university hardware. Seriously. So we can build this table, and this table will be a couple of gigs large, but that's not a problem, because nowadays hard disks, are so cheap and are terabyte sized. A couple of gigabytes just is nothing. Okay, so we can generate these tables. Okay, and using these tables, we can look up the config.secret value from the cookie that we obtained. Great. So now we know config.secret. Next steps. We would still like to predict the seed value that they used to initialize the random number generator when the reset, the password reset token was generated, right? Okay. As we have seen in the code, they use CRC to generate the seed out of microtime and the output of stat. So the next logical step would be to examine what CRC actually does. Okay, and this is what the next slides are going to cover. So CRC is short for cyclic redundancy check, and that's based on polynomials over F2, over the finite field F2. I guess most of you should know it, right? Okay. So the real short CRC primer. you have a message m, and you interpret this message as a polynomial over f2 by just taking the bits as coefficients. So that means, oh, I have an example here, so I will cover it later on. Then you take this polynomial and divide it by some fixed polynomial that depends on the CRC implementation. And the remainder of this operation is the CRC value. And that's basically it. So for instance, if you have this message here in binary, 11001, you would get this polynomial. 1 times x to the power of o plus 1 times x to the power of 1. Those are the first ones here. Then o times x to the power of 2. O times x to the power of 3. Those are the two o's. And then the last one, 1 times x to the power of 4. And this polynomial you divide by the generator polynomial, which is fixed for the respective CRC implementation. And then you get the CRC value out of it. And for some technical reasons, you also multiply the polynomial with some some large value, but that's only for technical reasons. That's not so interesting here. Okay, so this is how CRC works. And there is an interesting property. CRC is kind of additive. So that basically means if I have two messages, m and n, I can add up both CRC values and get as a resulting value the CRC of both messages added up. And when I say adding up, I of course mean adding up in F2. So add them up by coefficient by coefficient. So what you basically do is you XOR the messages when you add them up. You can easily check it by, if you add two polynomials, then you add the coefficients. In F2, adding is XOR. That's it. So that's an interesting property, especially when used in conjunction with cryptographic primitives. Because this is not something that we'd like to see when generating cryptographic secrets, because this is real linear, and linearities in cryptographic operations are not so popular. So what can we make of this property? Well, that this interesting additive property gives us one direct implication. Assume that we have some message m, but we don't know the message. We do know the CRC value. What we can do is we can generate CRC values of related messages where just a number of bits are flipped. So you have your message, flip some bits, and I can generate you the CRC value of your modified message, even without knowing the original message. That's interesting, because that we could actually use to take an influence on the CRC values that the random number generator uses. So if we manage to obtain one of those CRC values, then we might be able to predict further ones and to obtain the CRC values by using this addition trick here. So that's the basic idea. The attack would then look something like this. First, we reset our own password and obtain a token. We use the obtained token to get the CRC value that was used to initialize the random number generator. Okay, how do we do it? Well, that's the same thing as last time. We only have a limited amount of possible passwords that could have been used, and that's 2 to the power of 32 again. So the CRC value can be guessed, or we can look it up in some table that we could build. But this table needs to be installation specific because this one depends on config.secret. The password reset hash does depend on config.secret because they used the get hash function, as we have seen in the code some slides ago. So anyway, we are able to obtain the CRC value that was used to initialize the generator by looking it up in the table again. And as soon as we know the CRC value, we could try to compute future ones, because the input of the CRC function only depends on the time, and the time we can also measure. So that's the big overall plan. And then, of course, reset the password of the admin account and profit. So now we need to dig a bit deeper into how we can actually do it. The input of the CRC function that they used was this one here. So they took microtime, and they took the output of the stat function. For those of you who don't know, stat returns information about files in the file system. In this case, they query information about, I think it's even the very same file where the code is actually implemented in. But anyway, the output of stat contains tons of junk, like inode numbers, device numbers, file access times, couple of things. But interestingly, the only things that change in stat are the time values. So overall, between two calls to the random number generator, only the really time-related bits inside the microtime output and the stat output do change. The rest remains the same. And even more precisely, microtime is used in a string context here. That means that only the lower nibbles of the first few bytes can actually change, because the first few bytes contain the real microseconds, like the values that really rapidly change, and the later bytes then contain the real Unix timestamp. But the Unix timestamp only changes like from second to second, and this is quite slow, at least for an attacker, because the attacker can like make, I don't know, 100 queries per second. That's not unusual, and so we can safely assume that that the time resolution here is we can make multiple queries per second, and we don't need to pay attention to any time fields that are within a time resolution of seconds. So we only need to watch the microtime output, and this output we actually need to consider only the first few bytes. So the numerical representation, or the ASCII representation of those bytes, would be 0x30 or upwards. That would be the 0, 1, 2, 3, and so on. And we can see, due to the ASCII coding, only the lower nibbles do change between the numbers. So this is a 0, this is a 3 in ASCII. And so if you change from number to number, then only the lower nibbles change. Okay. If any of you guys has questions, or I don't know, wants another explanation, then just wave your hands. Okay. Here we have an example output of microtime. Microtime first returns the fraction of seconds. This is this one, and then the system time in seconds. And the last 2 bytes of the first part are quite often 0 due to the timer resolution on the respective systems. So that basically means if we manage to make 2 password reset requests within the same 10 milliseconds, then only this value, this value, this, and this could change. So because there are 10 milliseconds, if I'm not mistaken. And that again means we could represent the bits that actually changed by a bit mask, and that would be this one. First of all, some values that remain constant. Oh, sorry, that's my mistake. Within the same 10 milliseconds would be those values. And nobody realized. Okay, within the same 10 milliseconds would be those values that could actually change. So the bit mask that we get is a number of zeros for the first bytes because they are not going to change. Then this one here, because in the numerical values that change, only the lower nibbles can change. And then some zeros again, because the rest is constant. Okay, so we think, oh, that's awesome. Let's just compute the CRC value of the flipped bits and then add it up to the CRC value we already extracted. And that we can use to guess the CRC value that was used to initialize the generator when we reset the admin password. Yeah, kind of. The problem is, we just don't know the CRC value of the modified bit string here because we just don't know its length. The length of the string depends on the output of stat. And the output of stat we assume to be unable to predict. Okay, so another showstopper. So before we can actually proceed with our uber lead attack, we need to determine the length of the input to the CRC function. Okay, and that's the last mathematical part of it. So yeah, it's the last showstopper here. And man, it took me, I don't know, weeks or so to figure it out. So how can we determine the length of some CRC input? Well, that's not trivial. But this approach works. We can generate 2 tokens for our own account. And those tokens we receive via email, and that's not a problem. Then we can use our tables to find the CRC values that were used to initialize the generator when it generated our tokens. Also no problem. Okay. If we XOR the two CRC values, then we get the CRC value of the bit difference of the original inputs, because that's the additive property I mentioned earlier. And we further know that both CRC inputs have the same length. We don't know the length, but we know it's the same. And then again, the bit difference starts with some non-zero bits and has a large amount of 0 bits in the end, because only the first few bytes can change over the time. So the format of the bit difference of the CRC inputs is something like this. Okay, so we have the CRC value of the difference, and now we want to find the length of the input. Okay. Basically, we can form this equation here. The x to the power of 32 is only for technical CRC-related implementation reasons, not interesting here. What we have is our CRC value must be something like m, some message, times x to the power of some large value, because there are quite some 0 bits in the end. This is how the CRC value actually should look like. Oh yeah, and that's a modular reduction using the polynomial g. And keep in mind, those are all polynomials. M is a polynomial, x to the power of L is obviously a polynomial, and D is also a polynomial. Okay. So in order to solve the equation, we first need to find out how we can actually approach the x to the power of L and x to the power of 32, because D is the value we know and L is the value we want to know. And so we need to reorder this equation a bit. And this we do here. In case of CRC 32, the generator is an irreducible polynomial. That means that we can invert any polynomial in this ring. I guess most of you should know. We can even efficiently compute the inverted polynomials using the Euclidean algorithm. So it's safe to write this equation here, where we just use the inverse polynomial here, of x to the power of 32 plus L. The second step would be to overcome the modular reduction. Okay, how do we do it? I mentioned earlier that we assumed anyway that the attacker was able to make 2 requests within the same 10 milliseconds. If the attacker is able to do so, then only the very, very first few bytes or even bits may change. And that basically means that our unknown message here is smaller than the generator polynomial. And if it's smaller than the generator polynomial, it's absolutely safe to just completely omit the modular reduction and just write this equation here. And that looks a bit more friendly. But still, this is one equation, 2 unknowns, problem. We don't know M, we don't know L, but what we can try is we can just try to enumerate different values for L, just brute force it, and see if the resulting message M has the format that we expect. So what format do we expect? Well, we expect that only the lower nibbles of the first few bytes have bits set. So the upper nibbles of any bytes should be 0. And if this is not the case, then the L value is not the right one. So then we try the next L value and see if it has the right format and so on. This is, let me just go back one slide real quick. This is going to give us some candidates for L, because there might be multiple solutions. And if we get 2 or more candidates, what we can do is we can just repeat the process using other tokens, and then we can narrow down the values of L till we hit the right one. Okay. So the full attack looks something like this. You log into the target website and click Remember My Password. You take the cookie, use it to look up the config.secret value in your tables, and then you reset your own password a couple of times. Grab your own. After you reset your password, you immediately reset the admin password within like 10 milliseconds. You take your obtained tokens that you got via email and use them, again, using your tables, to obtain the CRC 32 values that were used to initialize the random number generator when the tokens were generated. And this is done using some installation-specific table, because those values depend on config.secret. Or you just brute force it, depending on how many NVIDIA GPUs you got. Anyway, once you have done it, you use the obtained CRC values to calculate the length of the input, because that's a constant. And once you know the length, you just try to brute force the bit differences in the CRC values that could have been used when the administrator's password was reset. Okay. So, and this is just some brute force search then. You just try CRC values, initialize your own generator, generate a password. From the password, generate a token using the secret value, and try the token on the website. And if it doesn't work, well, try again. The interesting point here is that there are no more than 16 bits. That means not more than 2 to the power of 16 tries. So that's the whole interesting point about this attack. Because, of course, we could try to just brute force the CRC value anyway, but it's 32 bits. And 32 bits would be like 4 gig tries. And 4 gig tries on a DSL line is quite much. You could use the university's internet. No, never mind. So yeah, you just perform your brute force search and then get some cold drink and wait until it hits the result. So that's so much for the theoretical part. Now I guess you want to see it fail. Let's try. Okay. Got the tables here on my external hard disk. Didn't fit onto my netbook's hard disk. Okay. So we launch up the script. Okay. And now it tells us, okay, it's getting the cookie. This is the cookie value. Now it's looking up the cookie value in the tables. Now you could see my hard disk blinking. And it's going to take a second or two. Yeah. And now it says, all right, this is the CRC value that was used to generate config.secret. And accordingly, can you all read that, actually? Because it's, I can imagine it's kind of small. Okay, no objections, then I'll just continue. The config.secret value is accordingly this one here. And for this config.secret value, we actually have pre-computed tables, surprise, surprise, because I built them. So we can continue. And now it requested a password reset for my own account. And I'm going to check my mail now. Okay, I've got 2 mails. Now it prompts me to enter the cookie. So I enter the token even. So now I enter the first one. And this is the second one. Okay. So now it's looking up the cookies and the according CRC values in its, okay, that was kind of fast, in its tables. And currently it's doing the modular arithmetics to determine the length of the CRC pre-image, which was found to be 180 bytes. Okay. Now it issued 2 password reset requests within like a very small amount of time. And one of those was for my own account, and the other one was for the admin's account. So now I should have mail again. Yep. So this is the last token I need to enter. Okay. Again, some table lookups. Okay. So the exploit is 2-staged. Now we are going to enter the actual brute forcing stage. So where it actually generates password reset tokens for the admin's account and tries them. So this is what we're going to do now. Okay. Okay. So now it says, okay, this one here is the correct token to reset the administrator's password account. And of course, I'm going to show you that it actually works. So I navigate to this URL. No. Yep, forgot my password. Admin. No. And this should be the token. Copy it here. Now cross your fingers. Yep. To complete the process, please enter a new password. So I enter my default password, foobar. Oops, sorry. Hope you didn't hear it. Okay, and now we can even try to log in, just to make it complete. Admin and the secret password. And voila, that's it. Now we can safely, hi admin, yep, we can safely overtake the site. Okay, so much for the demo. Just at the end, some conclusions. What actually went wrong here? For the typo 3 case that we have seen in the first demo, they shortened a MAC value without real proper reasons. Because I just assume we have enough bandwidth to transfer like the whole amount of 16 bytes. They're using the non-type-safe comparison operator, which in the end breaks their neck. And further, they forgot about the null byte problem in their check, where they wanted to prevent localconf.php from being downloaded. But the short MAC values and the non-type-safe comparison operator are the actual problems here. Because if the MAC value would have been larger, then we would have to spend more time to try and influence the value till it hits a numerical value. But this one is short enough to make it feasible. In Joomla, well, first of all, they used a weak random number generator, 32 bits of seed, no entropy accumulator. I mean, as a random number generator, that's a bad joke. Really shouldn't be used for cryptographical applications anyway. And then they even frequently reseed it, which is definitely not what they should do. And on the top of this, they use CRC32 for cryptographic purposes. And that's when you generate a seed for a random number generator, that's a cryptographic purpose, believe me. And using CRC32 for such a purpose, obviously without knowing what it actually does, is also not best practice. So I guess that's it. Yep. I'm done. So, oh no, okay. Then I'm ready for questions.